last time we proved the following theorems. The first Whitehead theorem is that if G is semi-simple Lie algebra finitely dimensional over some field, then first Whitehead theorem is that for any module, no, of course, finitely dimensional. First cohomology is 0, and second Whitehead theorem that for any finitely dimensional module, the second cohomology is 0. From the first theorem, through the observation that the first cohomology in coefficient in Hom is just the first x, and then they classify G-module extensions. Follow that theorem of Weil theorem, that any module of a semi-simple Lie algebra finitely dimensional is the sum of simple modules. Any representation is totally reducible, как будто вполне приводимо. It's the sum of completely reducible. Yes, completely reducible is the sum of irreducible subrepresentations. And from this theorem, we can obtain the second theorem. It was such implications. Okay, and the last, yes, and the first theorem was proved by Casimir element. We have Casimir element. It's from center of universal invariant algebra, and it acts by multiplication by rational number. Okay. And now from the second theorem, we can obtain Levi theorem. Levi theorem that if we have any finitely dimensional Lie algebra, then we have radical of Lie algebra is just the largest solvable ideal. If you have, no, Lie algebra is solvable if series Lie algebra G is solvable. If I consider G, then I consider commutant. It's subspace generated by all commutators. Then I can consider commutate of commutants, commutant of commutants, and so on. And if this series ends by 0, then we say that G is solvable. If you have two solvable ideals, then their sum is also solvable ideal. And so you can consider the sum of all solvable ideals, and it's also solvable ideals, the largest solvable ideal of G, and this is radical. It's largest, it contains any solvable ideal, largest, not maximal, it's largest solvable ideal. Solvable ideal. So G is semi-simple if it has no solvable ideal, so if its radical is 0. It's semi-simplicity. It's solvable, it's, yes, okay. And so Levi theorem says that for any Lie algebra, we have inclusion of solvable ideal, of radical. We have quotient. It's of course semi-simple Lie algebra. Okay, but Levi theorem says that this extension splits. So in fact, we have splitting. So in fact, G is semi-simple product of radical and some semi-simple Lie algebra. It's Levi factor, Levi quotient. No, Levi factor, okay. Some semi-simple Lie subalgebra of G also. Okay, let's check this.
What does it mean?
No, it's semi-simple. This means that this extension is splitting. So, no, as for groups, it's direct product as vector spaces, but no, this is ideal, this is not ideal. And if you, no, and you have action of this Lie algebra on this ideal, and this action is not trivial in general. If you want to consider commutant of two sums, some R plus L, R prime, L prime, no, then you have R prime, and then you have some actions. No, R L prime plus this means that This means that you have some subalgebra, Lie subalgebra, and any element of G is uniquely the sum of element of ADL and this subalgebra, okay? Any element G is sum of R plus L. And this is subalgebra. Of course, you can consider the vector subspace, but it's important that it's subalgebra. It's same simple subalgebra. If you consider commutant.
Yes, what about commutant?
No, commutant, it's commutant. It's commutant in radical, and this is something like this. This is commutant in subalgebra, and this is the action of L on R by commutant. It's of course action because it's subalgebra. Yes, it's as for groups. For groups, what is the semi-direct product? This means that you have two subgroups. Any element is a product of two elements, and one of this subgroup is normal. This is ideal. This is not normal. So these elements also are in radical. So this is the action of quotient on radical. It acts on radical because it's ideal. So this is from radical. This is from Lie algebra. This is your factorization of this commutant.
No, because I heard that in decomposition this is not direct sum of Lie algebras.
No, it's not a direct sum. Yes, it's not direct sum. Direct sum is when its action is zero. If they are orthogonal, yes, under a commutant, yes. If this action is zero, then it's a direct product. Semi-direct means that it's maybe not zero, but it is ideal, and any element is the sum of two elements. It's important that it's of course true that you have vector space. It's important that it's also Lie subalgebra. So this is some direct product of ideal or solvable ideal and semi-simple Lie subalgebra. So this extension has Lie algebra splitting. Of course, it has vector space splitting, but it's Lie algebra splitting. It's trivial extension in the sense of second homology, with some fixed action of this on this. Okay, now let's check this. This follows from the second Whitehead theorem, because the first case, if radical is abelian with zero commutant, then this extension is by. This means that. 1 second. Abelian. Yes. If it's abelian, this means that in fact this extension of some Lie algebra by some abelian Lie algebra, so abelian Lie algebra is just module of this Lie algebra. So this extension of semi-simple Lie algebra by some module. We know that this extension splits because it's classified by second homology. But here it's corresponding to extensions of the form of this form, where G acts on kernel, and on kernel we consider abelian Lie algebra structure. We have no commutant on M. So if this is our situation, then this splits just by second Whitehead theorem. So this is exactly this situation. If this is abelian, if it's no commutant on radical itself, then it is exactly this situation. Okay? No, it's by definition. If we consider extension of groups, we assume that this is abelian group. If we consider extension of Lie algebra, we assume that it's abelian Lie algebra and G mod, and this is G module. And then they classify by second homology. Okay? So now let's assume that radical is not abelian. Now then we will do induction by length, length of solvability of radical. Yes, radical is solvable Lie algebra, so it has a series of commutants and this is 0, no, minimal length is length of solvable algebra. If length is, no, I don't know, 1 or 0, then it's abelian. It's our base of induction. Okay, let's assume that we know this fact for any Lie algebra such that its radical has length k, or k minus 1. Okay. No, let's see. Okay, just consider commutant of radical of g. Commutant of radical of g. It's solvable algebra of length of the length of this radical is 1 less than length of radical itself. Okay. Okay. Now, just consider quotient by r. Quotient by r. No, yes. Consider something like this: radical quotient by r, g quotient by r. R is ideal in G also. This is all things are ideals in G. And our semi-simple quotient. Now, by induction. Not by induction. No, this is abelian. This is abelian thing. Abelian algebra. This is semi-simple, and the same semi-simple thing. So this thing is splits. We have splitting. We have splitting. So I have that this is.
Wait, what?
No, this is abelian. This is radical quotes by commutant of radical. So it's abelian algebra. It splits by just our base step. And this is semi-simple. It's the same semi-simple as our. We have only one semi-simple algebra here. It's our L.
What we did, we factored by r?
Yes. R is some ideal, and consider quotients of my of this sequence. It's some ideal in R. No, ideal in R, and it's also ideal in G. It's ideal in G, it lies in R, in radical. And I consider that quotient. Now it's abelian, so I have splitting. I have something like this. But now I know that now I consider this quotient as subalgebra of some Lie subalgebra of this thing. So in fact it has some this form where H is Lie subalgebra of G. It's isomorphic to our semi-simple Lie algebra. Because this quotient is sub-Lie algebra of this thing, it always has something of this form. And now we consider H, and for H is Lie subalgebra, and radical of H. Radical is sum of all solvable ideals. Now you can easily check that sum of all solvable ideals. It's just intersection of radical of G itself and this subalgebra. And this is exactly R. Because of this isomorphism. If I have some element which in H and in radical, this means that it's 0 in this quotient, so it means that it's in R. It's exactly R. So for H, I have our induction step. I have it's radical of H, it's R. H modulo R. And this means that by induction, solvable length of this radical is lower than length of our original radical. So I have splitting here. But now, this means that I have splitting here. Then I have splitting in my original sense, because this is my, it's isomorphic to radical and isomorphic to my Lie algebra L, and I have splitting L to H. And H it's just subalgebra of G, so I have splitting to G. It's what I wanted to construct by induction. The end. I want to construct it to the splitting. I construct splitting to some subalgebra. Which itself exists because of the splitting of abelian case. Okay, now you can think about this. This is the end of our Lie algebra story. Okay? Okay, now let's consider Hochschild homologic homology. Hochschild homology homology exists because non-commutative algebras exists. Yes, and if we have let A is associative algebra with unit over some field K for simplicity, or maybe over some ring in some situation, over field for simplicity. Так, что я тут хочу? No, then, if it's not commutative, then we have left modulus and right modulus over A. But then maybe M is a B module. A B module means that I have left multiplication by elements of M and right multiplication. And these two multiplication must commute. This is B module. No, of course, linear. It's left A module structure and right A module structure such that they commute. For example, because A itself is associative, A itself is AB module over itself. It's equivalent to say it's associative, if and only if it's AB module over itself. No, with the natural multiplication. Okay. Now I can consider. I can reformulate this. AB module structure, of course, it's just module structure over some other ring. As G module is a module over group ring, Lie algebra module is module over enveloping algebra, and B module is also module over some ring. So all these things is just modules over something. No, it's just something like AE. It's A tensor over K with A opposite. Opposite, it's algebra with the opposite multiplication. What if I have opposite multiplication? Is just multiplication in the opposite order. It's also associative algebra. I have two associative algebra, and this tensor product is also associative algebra as tensor product of associative algebras. No, without grading. It's just associative algebra. If I have two tensor products, I multiply them coordinate-wise. It's also associative algebra. No, and easy to see that B module structure is just module structure of this ring. A B module is the same thing as AE module. You can ask left or right module, but as for groups, left and right modules are in natural bijection because we have involution inversibility on the group, which sends left module to right module. For Lie algebras also, you have, I said this on the previous lecture, you have involution on enveloping algebra, which sends x from G to minus x. There exists such involution, and it also sends left module to right modules. And no, for this algebra, no, in general, left A module for any ring, left R module, is the same thing as right module over opposite ring. So this situation just say us that opposite ring for group ring is isomorphic to ring itself, and universal enveloping algebra opposite is also isomorphic to algebra. And this is isomorphic between these two. It sends one multiplication to another multiplication, these involutions. And for this ring, no, it's kind of tautologically isomorphic to opposite. Yes, because if you consider opposite, you obtain exactly the same ring. No, maybe with tensor product interchanging. So again, left and right modules are in very natural bijection. So it's just this module, left or right, it's the same thing. Structure of left and right module, it's the equivalent structures. If you have left module, it's right module. If it's right, it's left module by this natural bijection. Okay.
How do you multiply element M by A?
if, for example, it's left module, well then because of this multiplication inverse images, it will be a right module structure.
Wait.
Oh, okay. Multiplication in this thing, A tensor B, A prime tensor B prime. It's multiplication on the first, and multiplication on the right. But multiplication on the right is it's in inverse. Something like this. No, if this is considered as in A. No, okay, yes, no, yes, in this situation, yes, yes. Okay. Okay. No, and now for such associative algebras, you have A itself is associative algebra, and so if you consider some M is AB module, you can define Hochschild homology. It's Tor, no, Hochschild homology of A with coefficient in M. It's Tor or AE between A and M. Between A and M. No, cohomology it's X. From A to M is the definition for MB module. Now again, let's consider zero functor, derived functor of what they are. What is zero Hochschild homology of A M? No, it's just standard product. It's standard product over AE with A. What is this? No, this is no. Let me. It's easy access. Let me say what it is. It's M. No, it's kind of it's M modular commutant. AM. This is vector subspace generated by these things. M is B module, so we have left multiplication, right multiplication. It's not A submodule, so it's not. In general, it's not A modules. It's just K vector spaces, of course. It's not A modules. No, why? No, because no. For example, let's check that these things are zero in this standard product. No, it's because if I have let's consider A tensor M in this tensor. No, it's on the one hand, it's unit multiplied by from the left tensor M, and so this is unit tensor AM. But on the other side, it's unit from the left, and then by tensor product over AE, it's the same thing as A tensor MA effective, and we obtain equality. So all differences are zero. Now, and you can check that if you consider all differences are zero, then it's enough to all tensor product relations in the tensor product. No, it's easy consequences. Now you can check that all relations is kind of these relations. No, that's exercise. If you can check that what the tensor product over AE. Over AE. No, no, yes. Maybe. No, yes, something like this. Something like this. No, it's exercises. If you don't believe, it's an exercise. Think about this. Think about this. Think about what the tensor product over AE, what the relations in the tensor product, and you understand what this is, such relations. To understand, it's exercise. Understand tensor product over AE. No, it's just tensor product over some ring. No. Yes.
Yes, but why do we, when we multiply by A on the left, we need to act like AE module? No.
What?
We we need to consider A as an AE module, yes?
Yes.
But how we have a relation like that in our module? The vertical equality.
No, over any ring you have such relations, yes? MR, N, M, Rn, yes?
Yes, but here we need to use the action of our.
Yes, but in our situation we have two situations. It's also left and right models, and in the same thing it's right and left models. So we have such relations, and also you have symmetric relations. I just want to say something like this. By symmetry, no, it's not very obvious, but it's not very hard. You need to understand it by definition. No, it's
okay.
Of course.
Okay. So this makes more sense.
Of course. You need to understand that you have such two relations over AE, and these two relations means that you have the difference as 0.
Okay. Yes, this makes more sense.
Okay, sorry. Yes. Okay. No, and then the zero cohomology is dual thing. Zero cohomology, it's center of M. It's just such element such that AM equal to MA. No, center with respect to a module structure by the same argument. Okay, and so we have two such functors from AB module to vector spaces, K vector spaces, and this is derived functors of these two functors. This is right axis, left axis because it's home. No, yes, and this is home from A to M over AE. No, this is because M is just image of unit, and for unit you have such equality in A. A unit is equal to unit A, so this must be for any image of A. As always, as usual, home is easily understood than tensor product. Okay. Now how to compute them? We need some bimodule resolution, bimodule free resolution. But happily we already have it. It's bar resolution because it's bimodule, as I said before. It's not just module, it's bimodule resolution. Now let's remember this. Bar resolution. Which starts with A. A, it's over K. A, and so on. And this resolution is AB module resolution. If we have AB module structure from the left quotient and from the left factor and from the right factor, all these things are B modules, and all these differentials are B module differentials. No, let me remember. Let me recall. No, it's something like. No, and the last time it's -1 n a0 n -1 an, and if you multiply it from something from the right or something from the left, of course it's a linear from the left and from the right. It does not depend because the first quotient we multiply from the right, so it's linear with respect to multiplication from the left. And the last term we have multiplication with something from the left, so this operation is linear with respect to multiplication from the right. So it's AB module differentials, and this is. And now if we overfield any such thing, it's n-2. It's as AB module is amorphic to AE. It's this thing, tensor over A n-2. Overfield this is free vector space over K, so this is free module over AE with the same basis as this vector space over K. Okay, it's extension of scalar from vector space to AE module, just tensor product with AE itself. Now with this AE model structure. Okay, so this is free resolution. We know this is exact. No, exactness does not depend over which ring you consider these modules. It's just exact as vector spaces. Kernel is coincides with the images, so it's exact, free, and AB model. So this resolution of this, our model, what we wanted, we want a resolution of this model of AE. This is exactly this resolution.
Wait, this is isomorphism of what?
No, this is isomorphism of AEB modules.
AEB modules.
No, AE models, sorry, AEB models, yes.
Left AE modules.
No, yes, for example.
How do we act on the right?
On the right? On the right from this section.
Yes,
No, it's just no, in fact, this is just some kind of rewriting. This thing, it's the same thing. It's two pairs of A and n minus 1, n minus 2 A.
yes, it's two pairs of this and this as vector spaces, but as modules we need to.
No, module, yes. If no, it's the same thing as if you consider A tensor A as B module with the left multiplication on the left and right multiplication on the right. No, it's the same as AE as AE module. It's by definition, more or less. No, because in definition you consider OP, but OP no only say you that no the order of multiplication as vector spaces is the same thing. Okay.
As vector spaces is the same thing.
No, a module structure is just now I just emphasize module structure. Here it comes from left and right factors. Here it comes from this ring. No, it's just rewriting.
Okay.
It's to understand that this thing is free over this B module, over this module, over this ring. Sorry. Okay, so to compute homology and homology, we can use this bar resolution. The bar resolution. So Hochschild homology of A with coefficient in M is that homology of tensor product. For example, in my notes I use right model structure on M. So let me consider from the right over AE bar A and cohomology. It's cohomology of Hom from M B to M. Now let's consider it explicitly. Now tensor product. Now when we consider tensor product with M, no, of course I forget this resolvable, my resolved B model and consider only resolution itself. So M tensor over AE with this thing with AE tensor A minus 2. Now it's just M over K with A tensor n minus 2. So my resolution, my chain complex here, no, for example, homological one, has the following form: M tensor A, M tensor A squared, and so on. And what's the differential? Differential is the following thing. For example, 0, I don't know, it's not important. No, maybe it's not important, but okay. No, it's if it's n, it's n. Okay. Yes. Now then I have a right module structure. Then the same things, and then the last part. The last part is no, okay. If I have something like this, an minus 1 an, and the last part, or maybe no, yes, okay, and the last part, I again what from this. No, you need to. Okay, it's kind of also you can understand this. The last part is the again left model structure on M. And M. It's exactly from this interchanging. Because if I consider this AE model structure, then the last multiplication from the right becomes a multiplication from the left here, okay? On my AE module. No, in some sense, I can consider this that my M model here, my M model can stay on the left, and I consider right model structure. And here I can consider M, and at the same time that it stays on the last term from the right, and I consider left model structure here. This follows from understanding this isomorphism explicitly. Okay. No, because we need to use left and right model structures. No, this follows from this. If it's not obvious, if it's not clear, please think about this. Understand this. It's easy exercise. No, explicitly understand this isomorphism. So this is our chain complex, and its homology. It's Hochschild homology of M. No, and for cohomology, the same thing. I have hom from AE tensor A n minus 2 over AE to M. Of course, it's just hom over K from A tensor n minus 2 to M. So it's just functions in n minus 2 variables from A to M, and differential of something this form. We again have left multiplication of values of this function, and on the last term we have right multiplication. Sorry, left multiplication, the first right multiplication, something like this. No, so if we have such function, then differential of this function of n minus n, okay, is something like yes, but now maybe just 1 second. Yeah, no, yeah, the same thing. Yes, I have f a to n a1 minus 2 and the less than n minus 1. And in the middle terms, it's phi of a1 ai minus 1 ai a n minus 1. Okay, it's the same thing. Okay, or maybe here. No, okay, maybe it's here. It's from the left and here from the right. I'm not sure. No, okay, this is also an exercise. Okay, no, just consider explicitly what the difference. No, in fact, it's not. It really doesn't matter, because as I said before, left and right model structure is the same thing, so it's not very important. In fact, from the left and from the right, it also will be a differential, and it also will be a homology. For example, okay, let's consider what the first homology. No, first homology. What the first homology, for example, from this resolution is from explicit cocycles. What the first homology? No, yes, I think that this is no, this is more natural. I think this is right. This is right. So, what the first homology? I consider cocycles, cochain is map from. No, it's in fact. It's mapped from A to M. From A to M. Cocycle condition means that this is 0 and this is A, B plus phi AB. And minus phi AB. Yes. So cocycles is just so-called derivations. It's derivations. This is exactly derivations. It's map such with this property. It's one-dimensional cocycles. It's derivations from A to M to some B module. No, modular trivial derivation. Trivial derivation is if you have 0 cocycles, it's just element of M. Then d of M of A, no, it's just something like this. This is also derivation. This is no, inner derivation defined by an element of M. And so first homologies, all derivations modular inner derivation. So as usual. Okay. No, of course. Now we have second homology, and this is no. On the last lecture, I consider extension of Lie algebras, and we consider cocycles and so on. And now also the similar story. This is an exercise, but it's also easy. It follows easily as for groups and as for Lie algebras that second homology AM is defined by some second cocycles, and these second cocycles, of course, define extensions. It's extension in bijection with extensions of the following form: 0 M B A. It's extensions of associative algebras. Here M is associative algebra. A is also associative algebra. Is associative algebra morphism. M is associative algebra with so-called trivial multiplication, trivial squares. I have unit here. No, sorry. No, it has no unit. It's just with trivial multiplication. X, Y is 0. Yes, maybe so far it was not important that A has unit. So in fact, A has maybe has no unit. I think it was not. No, sorry. It's important for contractibility of partitions. Okay, A itself has unit, but M has no unit. It's just associative algebra with trivial multiplication. This is so-called square zero extension of associative algebras. I consider extension of some associative algebra by something with zero square zero multiplication. Okay.
So M is what?
M is AB module.
Yes, M is AB module.
If we have such extension, then M is always AB module because it's submodule. It's ideal in B, and if you can consider, you can multiply in B these elements by any preimages of A. And this multiplication does not depend on preimage because multiplication M itself is 0. You can for any element of A, you can consider some element of B which comes to A, and then consider, for example, this multiplication. And this multiplication does not depend on preimage because any other preimage is different. It's from N itself, and then because Mn is 0. Okay, this difference is from M.
So this is an extension of
associative algebras. Yes, associative algebra. If you have where you have again fixed AB module on the left. If you have this extension of algebra, and this is 0 multiplication, then always they think obtain some AB module structure of A. And if this AB module structure is fixed, then such extensions classified by second homology.
Okay, and A is always trivial.
Yes, of course. As for groups we consider abelian groups. For Lie algebras, we consider abelian Lie algebras. For associative algebras, we consider trivial multiplications. Yes. No, because on B module you have no multiplication in general. It's just B module. B module means that you have no extensions, so it's so-called square zero extensions, multiplication zero extensions, square zero extensions. No, this is the same thing. You can consider cocycle, and you can construct from cocycle this thing. And here, if you have such thing, you can consider vector space section, and from this obtain cocycle, and the same thing. Okay, now let's consider Kähler differentials for commutative algebra. Okay, let's consider. Let's A is commutative. Let's A is commutative.
So could you say again in the exercise, it is these extensions of modules?
It's extension of algebras, of associative algebras. It's all associative algebras. Associative algebras. But this algebra with zero multiplication, this is some algebra. It's this homomorphism of associative algebras. For groups, it was extension of groups, but this group was abelian. For Lie algebras, it was extension of Lie algebras, but this Lie algebra was abelian. This is extension of associative algebra, but this algebra with zero multiplication. Okay, if A is commutative, I can define first scalar differentials of A. No, it's just a module generated by these things. Its D is differential, yes. It's pairs of elements A and B from A modular relation that Leibniz rule. BC is just BDC, no, maybe B if you want, plus because it's commutative, it's no signs here. No such AB module. It's AB module generated by these pairs modular this relation. This relation is also a linear. It's a submodule generated by such differences. Okay. This module, now we have obvious map from A to omega 1A, since it's differential, since A to dA. And this is what's called derivation. Derivation, if you have commutative algebra, then B module is the same thing as module, because left and right just coincide. And module it's a module. So if you have some A module, then derivation, this is this thing. It's the same thing. Derivation. Derivation from some module is with this property. Now I just I don't see the difference between left and right multiplication. Such thing called the derivations with values in M, and so this is exactly derivation by definition. It's derivation with values in this A module, and this is universal derivation. So if we have any M, this is, let me call this dA. If I have any derivation, then there exists a unique A module map, such that this diagram is commutative. So derivations from A to M is the same thing as A module maps from omega to M. So omega 1 is co-representative module for this functor. Okay. I think it's more or less clear, yes? Okay. But what is this? What is this? Let me rewrite this definition of scalar differentials. As I said before, the numerator of this fraction is just module generated by pairs. It's just standard product of A and A itself over K. Yes, just A tensor A modular this relation. Let me rewrite this relation without symbol D. Okay, it's something like this. It's unit. Here it's dB is just element 1b. It's from the second quotient. Yes, it's from the second factor, and A coincide A tensor 1. So a relation has the following form: A tensor BC is equal to B tensor C plus C tensor what? Yes, C tensor B. Something like this. Now, of course, if this is true, then I can consider this is A module structure, A module. But if I want to obtain A module, I can consider all A multiplication from the left on this thing. If I consider A from A, I consider left multiplication by A from the left, then I obtain something like this. And now I can consider K vector space and A over K. This is the same thing, okay? No, it's A module, it is K module because I consider all A multiplication from the left, okay? But what is this? If I consider, for example, AB tensor C minus A tensor BC plus AC tensor B. Now this is exactly first Hochschild homology. Yes, because what the first Hochschild homology? First Hochschild homology, if I have some module M, I have M tensor A, then M tensor A, tensor A. And first Hochschild homology, I have M tensor A, it goes to MA minus AM here, and here M tensor A tensor B goes exactly to M A tensor B minus M tensor AB plus B M tensor A. And now in this situation, let M is A as B module itself, okay? If M is A, and in our situation, A is commutative. And commutativity just means that this differential is 0, yes? M is commutative means that this first differential is 0, no, maybe 0 differential is 0. So kernel is all itself, and quotient is by this difference. And this is exactly these differences. No modular some maybe some permutation, but our ring is commutative. So this is exactly first homology with coefficients in A itself, AA, between A and A. So we obtain this observation for commutative algebra that first homology is always is isomorphic to Cayley differentials, first Cayley differentials. Okay. On the other hand, let's compute first homology as we said, as we did before. First compute first homology with it's kind of trivial module. For Lie algebra and for group homology, it's what's abelianization. What is in this situation? Now we have such short-order sequence. What consider it's not this thing. It's not 0. We have multiplication here. Let me consider it mu. It's multiplication of A. Because A is commutative, this is A module map. AB module, A module, it's so on. No, A module. It's A module map. And I have ideal. This is short-order sequence of A modules. So A, B modules also. And so, of course, as for any short-order sequence, I have long-order sequence in homology and cohomology. Let's consider a long-order sequence in homology. And this is AE. It's free B module. So, as always, what we obtain? It's 0 A, then it's 0. No, it will be 0. Okay, it will be 0 because it's. No, sorry. Yeah, okay, ладно. A 0 A 0 A tensor A 0 A. And then first homology AA. And now this is 0 because this is the first homology of something free and something. This will be 0. Now we know what the 0 homology we know what is this. It's just M quote by commutant. Here, it's just A itself, because commutant in A is 0 because A is commutative. It's A itself. No, here it's also A itself because zero homology with ring itself, it's standard product with ring itself, it's module itself, always, okay? Zero homology with AE with something is just tensor product with EE over AE, so it's M itself. Okay. No, it's just I think it's a repetition of what we have done for groups and for Lie algebra, something like this. It's also A, and this map is identity. It's isomorphism. So we have what we have. Стоп. Что-то тут мне не нравится тогда. Нет, нормально, okay, yes. So we obtain that first homology with coefficient A isomorphic to zero homology of, sorry, it's with, yes, it's with coefficients, yes, sorry. Yes, I did not notice this on this situation because they are symmetric, so it's coefficients, it's our algebra, it's coefficients, yes. With coefficients in A. And we know what is this, it's M modulo commutant. It's EA modulo commutant.
Why is it isomorphism?
Because this is 0 and this is also isomorphic, so it's also 0.
Yes, but why?
What why?
Why do we have an isomorphism between?
This?
Yes.
No, by definition, no, you can unveil the definition of, for example, of resolution and obtain. No, this is A and this is also A and this. It sends A 1 to 1 if you want.
No, I mean the map can be arbitrary.
No, in this situation, this is explicit map and this is identity. It's exercise. Okay.
Okay, I believe.
Okay. No, it's map induced by multiplication. Yes. No, it's map induced by multiplication. So it sends unit to unit. Okay. So it sends unit to unit, and it's a module map. Okay. Now think about this. I think it follows from that it's map induced by multiplication, and multiplication sends unit to unit. And this is a module map also. No, of course you can check this is a module, no, but no, okay, no, okay. Let's do this if you want. Okay, it's an exercise, of course. No, such exercise was also for groups and for Lie algebra. It's the same price, I think. Check that in this situation when it's in general this in general if it's arbitrary module, this will be стоп, вот я что-то говорю не то, я что-то сказал не то, пардон. Да, что-то тут я вас немножко обманываю, пардон. Секунду. Так, zero homology of, sorry. Так, что я тут написал? Ну, точнее, написал неправильно, сейчас давайте исправлю. A with coefficients AE. Oh yes, it's just standard product with A over AE with AE is always A. Yes. No, yes. Yes, this will be A. It's A. No, yes, it's also yes. No, in general we have no such thing as A. No, yes, you can check that this is identity. No, explicitly from definition from this map and from I don't know for example from map on bar resolutions or something like this. Of course, it's identity. You check it. Okay, yes, it's an exercise. Okay. +1 in my list of exercises. Okay, and this is thing. But what is in general what this is absolutely similarly as for groups. Quotient by commutant is the same thing as M modular action of ideal, because this ideal this ideal is generated by such differences. Maybe I don't know. Do you believe in this, that this ideal is generated by such differences? No, it's no, yeah. The kernel of multiplication is defined by these differences.
Because it's commutative.
No, it's commutative, so this difference lies in ideal. I want to say that ideal generated by such differences is a module. No, it's easy exercise. It's what's also exercise. This exercise I have done. I know how it does, so I wanted to discuss. No, I think that it's also easier to give you as an exercise. No, it's easy exercise. It's easy exercise that as a module, EA is generated by something like this. Yes, something like this. In fact. Is a module. It will be important. No, if you consider because if you consider some element from tensor product, yes, let it go by multiplication. What does it mean that it lies in ideal? This means that multiplication AIBI is 0. Yes, it's multiplication. Okay. No, then I can consider minus AIBI tensor 1 because it's 0. Okay. No, and then if you consider this difference, you obtain something like AI 1 tensor BI minus BI tensor 1. Okay. And this is this thing. Okay. Okay, we have done this exercise. It's not exercise already. Okay. Something like this. So the thing is isomorphic to this quotient. Here, of course, we use that A is multiplicative. A is commutative because this a module map is defined only because A is commutative. But if A is commutative, we can define this ideal that this B module quotient is the same thing as this quotient because it's generated by A, B, B, A. It's generated by these elements. It's generated by 1B minus B1, and so 1B minus B1. If I apply M, it's exactly M. B, something like MB minus BM by definition of B model structure. So you obtain this isomorphism. Because ideal generated as a module by these things, this means that this is maybe exercise from definition of K. No, so what I want to say is that this thing is isomorphic as we say it for groups and for Lie algebras. This is A squared. No, it's as for general module, it's isomorphic to AM. If M is ideal itself, then okay.
It's I.
M is IA, yes.
I times M, yes. There.
Yes. Times. Вот. From geometric point of view, if you consider spectra of these commutative algebras, this will be diagonal. This will be inclusion of diagonal. And this will be a kind of normal bundle of diagonal. It's the same thing as a normal bundle of it's the same thing as cotangent bundle of X itself, and we see that yes, at least the first, it's the first differentials. Yes, we have seen that it's isomorphic to the first differentials. Yes. Oh. Now I compute this thing, and we obtain such isomorphism. Oh. Three things coincide. This is for commutative. No, because this thing is defined only for commutative algebras. For commutative algebras, it's cotangent bundle. It's normal for diagonal.
Why do we have 0 in the right of the sequence?
Mm-hmm.
We have 0 in the right.
Because this is HH1 of A with coefficients in free module. It's stored with free module, it's always 0 because it's E itself. Okay, it is free. AE is free B module, so all others free. This is the only non-free. It's A itself. All other this is only non-zero. This is A itself. All other are zeros. So in fact in all these situations we obtain HAI. It's isomorphic to A plus 1. This is true for I more than 0 for any A, and this is also true for 0 for commutative algebras because this is isomorphism.
Wait.
Mm-hmm.
So we have HH1
Mm-hmm.
A comma IA
Yes.
is isomorphic to HH1 AA.
Yes. Yes. Yes.
But
Yes.
if this is isomorphic, then the sequence is exact. Then this means that the second guy in the sequence is 0.
No. It's isomorphism. So it's 0 here. It's from 0. Its image is 0. It's the kernel of this next map.
It goes to 0 here.
Mm-hmm. Yes, this is 0 map because this is isomorphism. Mm-hmm. Okay. Yeah, this is ISO 0 ISO. Mm-hmm. Okay. Now, okay. So we obtain that for commutative algebras, the first scalar differential is the first Hochschild. No, the first Hochschild homology, and it's just I modulo I squared. I is cotangent bundle of diagonal, and I modulo I squared is just functions on diagonal modulo function squared. So it's just the first part of Taylor square. So it's first differentials on diagonal. It's the first differentials on X itself. Okay. Now. No, yes. Maybe what about algebraic geometry? Why Taylor differentials is important? Because you can define, for example, what if you have A is commutative algebra, then you have a fine algebraic variety, and you can define the Ramka homology as a homology of this the Riemann algebra. The Riemann algebra is exterior algebra on first scalar differentials. You have some A module. No, you have some module over your field. Yes. No, over A itself. Yes. And this is exterior algebra. It's algebra generated by by tensor product modulo such that interchange of order give you a sign. Yes. Gives you a sign. It's generated by element E1 En, where Ei is from omega 1, and sigma I sigma n sine. And if your base have two torsion, then you need, in fact, you need something to say that squared is 0. Okay. No, in fact, Okay. Вот. This is algebraic theorem cohomology. And for example, Grothendieck theorem. Grothendieck theorem. Grothendieck theorem that if X is smooth, yes, smooth, affine C variety, no, over complex numbers, then this algebraic theorem cohomology coincide with singular homology with C coefficient. No, so it coincides with differential theorem homology. So in fact, you have inclusion of theorem homology, smooth theorem homology. Oh no, algebraic theorem homology. No, any algebraic theorem form is kind of polynomial regular coefficients. Yes, so it includes two smooth theorem forms, and this map is quasi-isomorphism. What this theorem says, that this is quasi-isomorphism. On the oppositely, you can consider algebra. What does this mean? This is just, as I said before, it's exterior algebra over Kähler differentials. But you can consider smooth functions on X. It's also commutative algebra, and you can consider differentials on it and there, exterior algebra. And it's also maps to this, but this is of course not quasi-isomorphism. This is a lot of, it's not quasi-isomorphism. There are much more forms on this thing. So for example, on this, no, if you consider formally, no, this means that smoothly in smooth theorem complex you have some not algebraically formal relations. For example, something like this relation is not formal relation, which means that this relation does not hold in this algebra. In this algebra, you have no such relation because it's not algebraically; it's transcendental relation. It holds for any smooth. For example, for X is R. I don't know. For X is R. Okay, something like this, or C, if you want. This is transcendental relation. It does not follow from consider formally all algebras and consider formally only exterior relations algebraic. It's not false from them, so this is not true. So it's not quasi-isomorphic. You have some other relations. But if you consider smooth forms and all the things, it will be the same thing. So if you consider only algebraic form, then all relations between them are algebraic. If you consider transcendental form, not all relations between them are algebraic. Okay. But here, Grothendieck theorem says that if you consider only algebraic form, then all relations between them are algebraic and they coincide up to homology with smooth forms. For any formal forms with smooth coefficients, it's not true. It's not true. Okay. Now theorem, Hochschild-Kostant-Rosenberg theorem. Kostant-Rosenberg. Okay. Now let's again consider Hochschild homology. Hochschild homology of A itself. When we say it's A itself, then it's A with coefficient in A itself, between A and A. So it's homology of such chain complex. But this is not a bar resolution. It looks like bar resolution, but it's not bar resolution because it's bar resolution tensor with A. So differentials here is not exactly bar. It's bar with cyclicity. So it's differentials here A n. It's A0 A1 tensor minus A0 A1 A2 plus minus 1 n A n A0. Okay.
What do you mean with differential with different? It's the same differential.
No, it's not bar differential. Bar differentials will be that It's an minus 1, an, and this is n. It's not bar. It looks like bar resolution, but it's not bar. It's bar resolution already tensor over EA with A. It looks at the same thing, but it's not the same thing. No, it's differential as for M. Yes. It's kind of you kill one A and then shift. Okay. It looks like the same chain complex. No, it has the same modules, but another differential a little bit. Okay. It's with coefficient in A itself. Okay. Sigma acts on no. Okay. Let me denote this chain complex by something like CNA. Yes, it is C0, C1, C1. So sigma n acts on Cn. By permutation, all terms with except of the 0, 1. Because 0, 1 it's our module term and this is our bar terms. So yes, it's sigma on A0, A1, no, it's just permutation of all except of zero, 1. No, I write here sigma inverse because it's left left action. If you want right action, you can consider sigma. It's not important really. Okay. Do you agree that it's permutation of quotient of factors? Okay. And so I can define epsilon n CNA to itself. No, it's just sum with signs. It's just sum with signs. Okay, just permute bar terms and consider sum with signs. Okay, what the epsilon square?
Wait, what is written epsilon n?
Epsilon n.
What is this?
It's just sum of all these actions with signs in each element of my CN, and then by linearity, because sum goes to sum. Mm-hmm.
What's called ni?
Where is ni?
Epsilon. What is written? Epsilon. Epsilon.
Epsilon n.
Okay.
It's on n. Yes, on n. Okay. What's the epsilon squared? No, of course not. If you symmetrize and then symmetrize again, what you obtain?
Itself.
It's kind of symmetrization. No, it's symmetrization, but after the first symmetrization, you already obtain symmetric tensor. And if you symmetrize symmetric tensor, if you consider, it's just not symmetrization, it's symmetrization without dividing by n factorial. So you obtain n factorial, n factorial identical terms, yes? So it's n factorial symmetrization, okay? Okay. Now I can define the following map. In this theorem will be a lot of exercises about explicit calculations. They are really explicit. I can define the following thing: A tensor serial algebra over K of A to CNA. Just sending A0 tensor A1 AN to epsilon n A0 A1. Oh, sorry, it's not symmetrization, it's skew-symmetrization, yes. It's skew-symmetrization, so if you have some skew-symmetric thing, it's, this thing argues with so it respects skew-symmetric relations here, okay? Because skew-symmetrization respects skew-symmetric relations. Mm-hmm. If you have interchange of some terms here, it will be a sign. Mm-hmm. And here it will be a sign also. Mm-hmm. So it's equal to minus A2, A1, and this is also, if I have interchange here, it will be a minus, because it's skew-symmetrization.
Okay, it's called.
Okay. Now I need a Chevalier-Lemberg complex for Lie algebras, as which was on the previous lecture. Well, let me recall this. If I have Lie algebra, then I have Chevalier-Lemberg complex of Lie algebra. It's tensor product of universal enveloping algebra and exterior product of exterior algebra of this Lie algebra over K, and my differential was of two parts. Differential of some element U from universal enveloping algebra and some exterior product is just the following thing. The first part is something like this: xi tensor x1 without xi plus some I less than j minus 1 I plus j u tensor commutator x I xj without xi without xj. It was an exercise that this is differential. The square is 0. It's an important exercise. I will ask you if you obtain a ticket about Chevalier-Lemberg complex. It's a direct exercise to obtain that it's differential, and we have proved that this is a resolution. That in fact this chain complex is exact. We have proved this. You need to check that this is differential 0, square 0. We have proved that it's exact. So this is free resolution of K over G. So you can calculate homology of Lie algebra with this thing. And now I want to consider the following thing. For example, if you want to compute homology of Lie algebra with coefficient in some module, then you need to consider this resolution and then tensor it with M over UG. So you obtain homology of M tensor over K with exterior algebra over G just. No, and differential have the same formula where I just replace element of M here. It's element of M. Okay. What? Tensor M over G is just M. And now this complex computes you homology of G with coefficient M. Okay, for Lie algebra. Now I want to consider if A is associative algebra. I can consider A is a Lie algebra over with commutator. It's Lie algebra with commutator is associative commutator. And I can consider homology of this Lie algebra with coefficient in A itself, because any Lie algebra is Lie module over itself with commutator as an action. So I consider here it's A over A. Over A. This is just A over K with this thing. Вот она, the same thing. And on this thing I have Chevalier-Lemberg differential. Chevalier-Lemberg differential here is what is A is 0, yes? Let me check. A1, An. And here I have the right action, it's just by commutator. It's just A0, AI, A1 without AI, An. No, and here the same thing. It's A0, and this is commutator. AI, AJ, commutator in associative algebra without AI, without AJ. So what I want to say is that I have differential on this thing. And so an exercise that this map is a chain map. It's with Chevalier-Lemberg differential here and Hochschild differential here. Epsilon respects the differentials. No, it's more or less explicit computation. That no a tensor a epsilon a. If I have here Hochschild differential, here I have Chevalier-Enberg differential. This diagram is commute. It's kind of combinatorial exercise because you have explicit formulas. Okay. Now, if you believe in this exercise, then let me assume that A is commutative. It works for any associative algebra. But if A is commutative, then it's abelian algebra. It has 0 commutators. So all these commutators are 0. So Chevalier-Enberg differential is 0. So Chevalier-Enberg differential is 0. And this means that this epsilon, so this means that induced map on homology just sends, no, homology is the same thing to Hochschild homology. Okay? That epsilon induced map on homology from A to A itself, it's a homology with 0 differentials to Hochschild homology. Okay? Do you agree? No, if A is commutative, then this differential is just 0, so homology coincides with this chain complex itself. And so because epsilon is chain map, it's induced map on homology. So it sends homology of the left, it's the same thing to homology of the right. Okay? Okay. Now the last, but not the least. No, the most important maybe exercise. It is kind of explicit exercise. But here it's important exercise. No, here it's just formulas. But no, this is also formulas. But maybe I will say something about this exercise. Where is scalar differentials here? Where is scalar differentials here? No, okay. What I have? I have A tensor A epsilon to Hochschild homology. And here I have, okay, here I have natural map to scalar differentials, P, which sends, no, in kind of tautological, just A, no. Kind of this. And so excite that this map quotes from through this map. So there exists this map. So my claim is that epsilon bar respects relations on scalar differential. So it respects no, if I have some relation on scalar differential, so this goes to 0, then epsilon bar also sends it to 0. No, it's kind of explicit checking. No, maybe let me say something about this. Surprisingly. No, for example, why it's true? Why it's true? No, and this map I also will denote by epsilon. For example, what relations in scalar differentials we have? No, for example, we have something like this. Minus dA2 plus a d2 plus a2 plus a2 dA1 is 0. Yes. So I can multiply it by something. A3 d3 dan plus a1 da2 a3 dan plus A2, dA1, dA3. In fact, it's kind of all relations of such form, yes, in Kähler differentials. So we need to check that this, no, what image of what this? This is image of the following thing, of the same thing. It's minus A1, A2, tensor A3, tensor tensor n, plus A2, tensor A2, A8. No, da, yes, okay, it's true, but no, in general, in Kähler differential, you have also something like A0 here. A0, A0, A0. Maybe something like this. No, and then this is just, okay, yes, this is just, yes, this is just minus A0 tensor with this, then A0, A1 tensor, A2 tensor AN, and plus A0, A2 tensor A1 tensor A3 tensor AN. Do you agree? I consider some relation in Kähler differential. It's some of this form. No, it's following of my generating relation. It's my generating relation in my Kähler differential. I have some relation of this form. This thing is image of this thing under P. So what I need to check now, that these things goes to 0 by epsilon bar. Then, so if some element goes to 0, no, if some element goes to 0 here, then it must go to 0 here if I want some factorization, yes? It's more or less the same thing, yes? It's just kind of kernel of P lies on kernel of epsilon bar. It must be something like this. No, so this thing, it goes to 0. It's 0 in my kernel differential. So no, yes, and now if I go this to by epsilon bar, no, it goes to 0 in homology. No, in fact, it goes to boundary of something. Boundary of what? No, let me write down boundary of what? Epsilon bar of this thing. So epsilon bar is 0 homology class. It's important that we consider homology class here. It's not factorization to chain complex. It's only for homology. So this is not 0. It's 0 in homology. So epsilon bar of the thing is boundary. Boundary of what? No, it's boundary. It's minus boundary of no something like this. Something like this. Sum of sigma from sigma, where of such permutations where image of the first less than image of the second. Sine, and now sine of yes, 0, 1, something like this. What? Now you can now you can directly check that differential of this thing is exactly this thing. And if you do this, you obtain that relations in Kähler differentials goes to 0 in homology. So this map factorized through Kähler differentials. Okay. No, this is my kind of hint to this for this exercise. Okay. Sketch of proof of this exercise. Okay, now we obtain finally this map from Kähler differentials to Hochschild-Kostant-Rosenberg. It's our comparison map. It's called Hochschild-Kostant-Rosenberg map. We will check that this map is isomorphism. No, the first step, if you want to obtain the two things isomorphic, the first step is to construct map between them. Okay, this is the map. In fact, we have map on the opposite direction, of course. Maybe okay. Actually, we have map from Hochschild complex to Kähler differentials. two Kähler differentials pi. No, it's also kind of tautological. It sends a to a0. No, again, dA1, dAn. And now it's kind of more explicit calculations and check that pi differential is 0. It's always 0. It's pi and then differentials. And on the opposite. No, pi of differentials. You have differential and then pi, you obtain 0. You obtain 0. I don't consider the RAM differential on the RAM, so I have only differential here. So if you consider boundary, then pi of boundary is 0. No, it's kind of, no, it's in the same matter. So no, it says that boundary is the same thing, more or less the same thing as scalar relations. Scalar relations. Okay. So what we obtain? We obtain that. Okay. Now again, from this we obtain that if you consider 0 differential here, we obtain the map from homology to Kähler differential. Pi. What the composition of epsilon and pi? What the composition of epsilon of pi and pi? No, epsilon is Q symmetrization, is sum of these things with signs. But any of these things goes to the same form up to sign, and we have sign here. So in fact, this thing goes to n factorial the same form. It's n factorial pi n. No, because scalar differential is already skew symmetric. So skew symmetrization does nothing. Okay, does nothing, and we have sum of n factorial identity terms again. So now what we obtain? We obtain that. What we obtain now? Let me assume that characteristic is 0. It's important here. What we obtain? What does it mean? We have Hochschild homology. We have Kähler differentials, and we have that. Yes, we have. Just stop. No, sorry. Identity, of course. Sorry. Yes, we have that pi epsilon. No. Epsilon pi is identity, n factorial identity. Out here is n factorial identity. But because we over characteristic 0, this is isomorphism. Yes. What does it mean? What does it mean? If you have two, I don't know, vector spaces or modules. And you have two maps, and one composition in one direction is, for example, identity. What does it mean? It means that it's direct summand, yes? What direct summand of what? No, which one of these maps is monomorphism? Yes. This means that this is inclusion of direct summand, and this is kind of surjection. No, if we divide by n factorial, for example. Okay, now we need to check that this inclusion is isomorphism. To do this, we need two lemmas about algebra. One lemma about purely algebra and one lemma about causal resolution. It was an exercise, but maybe I'll do it now. The first, it's easier thing. First thing is if you have map between two modules of a commutative ring, and then its isomorphism. Значит, это over commutative ring is important. Over commutative A. This isomorphism if and only if for any maximal ideal in A, localizations are isomorphism. It's also true for monomorphism and for epimorphism. No, in fact, it's because. Do you remember what the localization in maximal ideal? I consider all fractions with denominators are elements not in this maximal ideal. It's mx, where m is from M, and x is from A without maximal ideal. Okay. And if on these fractions it's isomorphism for all maximal ideals, then it's isomorphism on original modules. Okay? Значит, why it's true? Because localization, any localization, it's standard product with A localized with M. It's a ring of fractions. All such modules are flat, yes, are flat over A. So all these localizations are exact. Localizations are exact. So in fact, kernel localization of kernel is kernel of localization. It commutes with homology. So kernel of F localized is kernel of M localized, and image also. So in fact, this is corollary of the following fact, that M is 0 if and only all localizations are 0. No, of course it's equivalent formulation. No, okay. Now why it's true? No, because it's more or less obvious. Because if you have x from M, now consider its annihilator. It's ideal in A. Well, if x is not 0, then this annihilator is not whole A. Okay, this is proper ideal. It is this not 0 if and only not equal to A if and only if x not equal to 0. Okay, because A consists unit, contains unit. Okay. So if it's not 0 element, then I have some non-trivial ideal, and it lies in maximal ideal. And now, if I localize in this maximal ideal my module, it will be 0. This means that that my fraction x1 is equal to 0, 1 in this localization. Now, this means, by definition of localization, that there exists y from localization from maximal ideal such that what I consider x1 minus 0, 1, and then I multiply by some element from, not from a localization element, not from my ideal, such that it's 0. Now this means that yx is 0, but y is not maximal ideal, so it's not from annihilator. So it's something wrong here. It can't be happen. So any element must be 0. No, or maybe this ideal it's A itself. No, localization of A itself it contains 0, so it's kind of 0 ring. We do not contain this. Okay. Okay. From this and from your exercises about flatness of localization, it follows that it's enough to check that localizations of our map, because we are over a complete ring, are isomorphisms. We have explicit map, so it's enough to check localization in maximal ideals. Okay. The first step. The last step, the second step. The second step is the following. It's an exercise. If I have commutative ring, and I have if I have commutative ring and I have some ideal generated by regular sequence. Generated by regular sequence. Generated by regular sequence. Then it was an exercise that what is the Tor over R between Ri and Ri. Did you do this exercise? It's about exterior product. And did you do this? It isomorphic to exterior product. Exterior product of I squared of this module. Sorry, over I. Yeah. We have an exercise that Tor 1 between R modulo I and R modulo J always isomorphic to I with J, Ij. No, if I is equal to J, then we obtain I modulo I squared. It's always true. But if I generated by a regular sequence is true more generally, that all higher torts is just exterior product of this I modulo I squared. Okay, let's check this. Let's do this exercise because it's our last lecture and we have some time and we have a seminar before this lecture. So let's do this exercise. Okay, now let's do this by definition. What the Tor? To compute Tor, what we need to compute the Tor? We need resolution. Yes? We need resolution, free resolution. For example, what the free resolution of quotient ring we know. Especially if I is generated by a regular sequence. It's Koszul resolution. It's our original Koszul resolution by exterior product of R itself. It's if I is generated by a regular sequence, regular ideal, so it's more or less equivalent, then Ri have Koszul resolution. It's lambda R, where differential acts, no, it sends, I don't know, u, no, d, I know, du to xi. No, remember this from Koszul resolution. Okay. No, so yes. So what the tensor product of this Koszul resolution with the Ri itself? Then we will compute homologies. Yes, let me recall that this is of Rn. N is number of generators of our ideal. Yeah, this is exterior product of this free module. So Koszul resolution, for example, K I tensor with Ri or R with tensor K of Rn over R Ri. What is this? If you have exterior product of some module and then tensor it with some ring. No, it's maybe an exercise, but no, it's kind of exercise, but it's more or less obvious. Now what we obtain? If you have extension, if you have some module, then you for any module you can define exterior product. Maybe no, more or less by the same thing. It will be in exercise, okay. But if it's module over R, then if you extend scalars, what I obtain? No, of course I obtain exterior product over extension of scalars. Yes. It will be an exercise, and the definition of exterior product of module will be in the list of exercises. No, it's more or less kind of clear. I think it's more or less believable. Yes. No, for example, what the exterior product? Yes. So this thing is just exterior product of Ri(n), okay, as Ri module, And now, no, yes, and no, so what the direct sum of quotients? It's I. Yeah. The same thing. And now, what's important thing? It's not now. It's over R and I. So I. Important thing. We will check it now. That this thing is just isomorphic to Ri, to I squared. Isomorphic to I squared. But okay, but this is just our tensor product of our resolution with Ri. Now we also have some differential. Where is differential? But claim that differential here is 0. The induced differential is 0. It's because what our differential? Our differential, as I said before, if this is some exterior algebra of some free module. It's exterior algebra of some generators. Yes. But by definition of our Koszul resolution, Koszul differential of our generator is xi by definition. So induced differential sends ui unit to xi unit. This is xi. It's unit xi. But xi is 0 in this ring. Okay. So of course differential here is 0. My Koszul differential, its image is in I, lies in I. Image of my differential lies in I. So of course, if I tensor with R modulo I, my induced differential will be 0. Okay. Because image of my differential lies in I, and I in this tensor product, if I can interchange I from this to this, and this will be 0. Okay. Okay. So differential 0, and we only need to check that this is isomorphic. This is also true only for ideals generated by regular sequence. It's not general. It's not generally true. And this will be the answer. So we need to check that if we consider the same ideals here, then the differential is 0. In general, it's not 0, and you obtain that the difference between kernel in the image of this differential is something like this. Something like this. This is exactly because in fact when we proved this, it will be something like yes. If you consider another differential, you exactly obtain something like difference between intersection and I itself, and intersection with Ig, something like this. Something like this is the difference. It's kernel, and image is kind of Ij. Okay. It was the previous exercise. In this situation, this is exactly 0. Is it clear? The differential on this tensor product is 0. If you consider Koszul resolution, then tensor it with Ri, then induced differential is 0. Okay? You need to consider the definition of Koszul resolution and then obtain that this is 0. So homology Tor is the same thing as this thing, and we only need this isomorphism. Our final is isomorphism. Why this isomorphism is true? Why this isomorphism holds? Okay, consider the general situation. This situation. So what we have? We have Rn goes to I. Since multiplication by x time. Standard basis goes to generators, to regular sequence. And we have some kernel of this map, some relations of my ideal. Also I have ideals here. If I consider n ideals, then multiply it to xi. I obtain I squared exactly. And here is some also the kernel. And here I have n I squared, and this is my question. my claim that this is 0. This is isomorphism. Okay? Do you agree? I is generated by x1, x7. Regular sequence. Okay? I have this diagram, I have some kernels. No, and my claim that this is 0. So this is not just epimorphism, this is isomorphism. Okay? No, what does it mean? This is 0. This means that this map is epimorphism, that any element of kernel here is image of kernel from here. No, okay, but no, what the kernel of this map? No, we know this, in fact, because no, because we have our Koszul resolution again. Ri, it's R, it's I, and here is exactly our map. Rn, it's xi, it's our lambda 1 of Rn. It's our first step of our Koszul resolution. We know that the kernel, it's image of lambda square Rn. We know that the kernel is the image of this differential. And this Koszul differential sends u1, u2 to x1, u2 minus x2, u1, something like this. Now, what this means now u2 and u1 is just some basic elements of this free module. So this differential, in fact, we see that that kernel, that kernel of this map, K2, is just generated by such rows xi minus xj 0. This is j, this is I number. No, of course, this is in kernels, because if you consider such element and then multiply k element by xk, you obtain 0. xi xj minus xj xi is 0. But Koszul resolution says that this is that such relations generate all relations, because image of such relations generate all kernel of this map. This is statement of Koszul resolutions of exactness of Koszul resolution, and the exactness of Koszul resolution is equivalent to say that regularity of sequence is important here. That X sequence is regular. But if this is true, then all these relations generate K2. But these relations also comes from this, because these relations in fact lies in K1, because these elements lies in I. So this row lies in fact not in this but in this, and it's also in kernel, of course. So in fact, this thing lies in Rn, but in fact it lies in In. So in fact this row lies not in K2 but in K1, and so it's in image of K1. So this map is surjective and this is 0. Okay. So yes, okay. We have two steps. And let's combine them together. Let's prove. Okay, let's consider our multiplication map for our commutative algebra. Let's consider M is a maximal ideal in A. And this is, we have kernel. kernel I, what we have that homology N A, Hochschild homology. So by definition is store, but let me denote this commutative ring by R. It's store over R between A and A, yes? But A is R modulo I. So it's store R, Ri, Ri. Okay? On the other hand, scalar differentials homology is by definition exterior algebra over A, so over R modulo I, of over omega 1, but as we see before, this is I modulo I squared. And we want to check that these things are isomorphic. But in general, they're not isomorphic. What's the problem? The problem that in general, I, of course, is not generated by regular sequence. It was an important thing. These things are isomorphic if I is generated by regular sequence. It's very important. It's not true in general, of course. But, okay, now let me consider any maximal ideal in A. And, and we have some maps. Some map here, map here. Let's consider localization in our maximal ideal. It's because A is commutative, this is A modules. We can consider localizations. And what we obtain? Localization, what we obtain? For example, okay, what we obtain? Now it's not equal here, but it will be equal from on the right. Localizations. No, localization is exact functor. So what we obtain here, it's store. It's store. Over localization, we have maximal ideal here. Let's consider its pre-image. It's some ideal here. In general, maybe not maximal, yes? Or maybe, in general, maybe not maximal, but it's not important here. But localization is exact. It's kind of exercise from the beginner of our thinking about exactness of localization, maybe. So it will be localization of R in pre-image of M. And here is localization A, M, A, M. Or maybe not such thing. It's just it's R. Сейчас, мне нужно, наверное, переобозначить. Ну ладно, в общем, M модуля I. В общем, все локализации, которые тут есть. Локализуем в том, в чем есть. I have ideal M on the right, and I have ideal mu, pre-image of mu on the left, here and here. On the other hand, this thing is isomorphic, the same thing. It's just L mu minus M, mu minus M, M squared. Because it's also exact. And now we need that this is isomorphism after localization. And this is now a theorem. Now theorem is kind of technical. If A is commutative, and for any maximal ideal localization in pre-image is generated by regular sequence. Then Hochschild homology is isomorphic to Keller differentials. It's Hochschild-Kostant-Rosenberg Theorem. We proved exactly this, because if this ideal is generated by regular sequence, we know that this is isomorphic, and of course now you easily can check that this map is the isomorphism here. It's exactly the isomorphism. We know that they are isomorphic, and the isomorphism is this map, for example.
And this is always isomorphic.
Hmm?
And this is always an isomorphism.
No, this is we obtain that this is isomorphism after localization in any maximal ideal. Then this is isomorphism, as I said, as step 1. If some modular map is isomorphism after localization in any maximal ideal, then it's isomorphism. We only need to check that this is isomorphism after localization in any maximal ideal. No, if after localization we obtain ideal generated by regular sequence, this is true. Now, what the localization in maximal ideal? It's kind of localization in some closed point of your scheme. Yes, maximal ideals corresponds to closed points on your variety, to get geometric points. And if in this geometric point your ideal is generated by regular sequence, it's this. Now, no, let me reformulate. This is equivalent to say that A is smooth. It's equivalent formulation. This means that locally your variety kind of generated by intersection of smooth functions. It's kind of smooth. Now, of course, so we proved this. This is proof. Now let me reformulate this notation. No, it's story of algebraic geometry, but of course it's all equivalent to say. It's kind of general notion of smoothness. General notion of smoothness. We have already proved it. Because we say and we need to check only that this map is isomorphic. But we know that this is isomorphic. No, for example, if they find the dimensional of a vector space, then we know that this is a direct summand and they are isomorphic. No, if it's not finely dimensional vector space, then you can check that exactly this map gives you the same isomorphism as we say it abstractly, as we see it abstractly. So if we only need that ideal generated by regular sequence. If it's true, then we know that it's more or less we know that it's isomorphic. Okay. Now I want to reformulate just this smoothness property. This smoothness property. For example, A equals smooth in general if it's algebra over some commutative ring R. Commutative algebra over commutative ring R. It's smooth if A is R flat. No, flat as R model. In our situation, it's true because we consider the situation of field. And for any maximal ideal, localization of diagonal ideal is generated by regular sequence. So we proved, in this definition, we proved exactly for smooth commutative algebras of a field, for example, of a field of characteristic 0. Yes, I said it at the moment. Now, for example, if our ring R is Noetherian, for example, field in our situation, Noetherian, and A is of finite type, for example, finitely generated. Then in this situation, so of a field for finitely generated algebras, yes, this is equivalent to say that it's smooth in our usual case. For example, it's Jacobi criterion, yes, Jacobi criterion of smoothness, Jacobi criterion. If you consider that if you represent your algebra as polynomials modular some relations, yes, then in each closed point, no, Jacobi matrix will have co-rank equal to dimension of your manifold, of your variety, something like this. It's our usual annotation of smoothness. So it's the same thing as spec smooth in our usual notion. No, it's the same thing, for example, that our omega 1a is projective. Projective of rank equal to dimension of A. This means that in any closed points, localization is free module of the same rank as dimension. So locally, it's locally free module. So it's projective module. It's locally. In general, it's a sheaf, and this sheaf is locally free. It's a vector bundle in each point. It's equivalent for each point. If one point this thing is equivalent, we say that point is smooth. If it's true for any point, we say that our scheme is smooth. And for such situation, we proved that over characteristic 0, Hochschild homology coincides with the RAM homology, so the RAM form. So it's kind of generalization of the RAM forms. So it's true for commutative algebra. For not commutative, this has sense. So it's kind of non-commutative generalization of the RAM homology of the RAM form. So it's kind of non-commutative the RAM forms, non-commutative geometry, and so on. You can talk with Koledin about this, something like this.
You said that being projective a module is the same as being free after.
Yes. No, this is general fact. Module is free, projective if only if localization in any maximal ideal is free. Yes. No, free, and now it's important that it's of rank equal to dimension. Yes. In general, you can define for not only affine scheme. You can define for any scheme kind of sheaves of Hochschild homology and sheaf of forms. And in characteristic 0 for smooth schemes, not affine, but for any schemes, it's also isomorphic. So it's in general this is true. This is kind of yes, this is true for not only for affine scheme, but in positive characteristic, at first it's not true for not smooth. For not smooth is not true. It's in zero characteristic also it's not true. It's important smoothness here. In positive characteristic, this thing is also not true for not affine varieties. It's not true. It will be counterexample. But for affine variety, for algebras, for smooth algebras in positive, is this also true? No, but it needs another proof, but it follows from some general nonsense. No, so this is the direct geometric map, very natural map, and observation that this is true for affine varieties of a characteristic 0. What should be done? Okay, and maybe the last thing about this will be about Hochschild homology in algebra and algebraic geometry, so on. It's a kind of non-commutative generalization of the RAM forms of schemes. Now, one word about Hochschild homology in topology, in algebraic topology. In algebraic topology, Hochschild homology also interesting because of the point of view of the following theorem of Jones. Now, of course, we will not prove them. It proves by Eilenberg-Moore spectral sequence, for example. We discussed it a little bit. Now, from this, you can prove this, in fact. It's the following theorem. If you consider topological space X, simply connected, one connected, for simplicity, then you can consider co-chain algebra. It's associative algebra with cup product. It's not commutative, but it's graded and associative. You can a little bit change definition. You can define Hochschild homology for graded algebras also. For graded and differential, it's differential graded algebra. But you can you have bar resolution for differential graded algebras, and so it will be your definition of Hochschild homology of differential graded algebras. It's not the problem here. And if you consider this is differential graded algebra, associative, if you consider Hochschild homology of this algebra, theorem of Jones says that this will be cohomology of the space of free loop. Space from continuous maps from circle to X without base point. It's space of free loops, and homology of free loops is Hochschild homology. No, also you can in fact you can define product here because no, at least as abelian groups. So Hochschild homology is functor which it's co-chain complex of X itself and give you chain complex which homology is homology of free loop space. No, it's kind of in fact Hochschild complex is kind of co-chain complex of free loop space in some simplicial incarnation. For example, if M is manifold, is smooth manifold. Now, of course, you can use not co-chain but de Rham complex. You can consider de Rham form, de Rham complex, and it will be also a homology of free loop space on smooth manifold. No, you can consider. I think it. This theorem, I think it's proved in Weibel. I hope, I believe. It follows from Eilenberg-Moore spectral sequence in general. You consider. Ну, it's. Там он в общих словах, он же не топологическая книжка, но вообще у него там в общих словах там что-то доказывается, там он что-то говорит, что он чуть машет руками, говорит, что там у нас есть топологическая интерпретация, топологическая там модель того и того пространства, и там есть Eilenberg-Moore, который их сравнивает, и видно, что вырождается. Ну окей, this is all, folks.